All right, welcome everybody. Today we're going to talk about Calc Lesson number 59, and this is an introduction to Chapter 5. Chapter 5 is a chapter all about finding derivatives and finding integrals for both exponential functions and logarithms. Now, exponentials and logarithms is a topic you should remember relatively well. You saw quite a bit of it in Algebra 2 and quite a bit of it last year in pre-calc. To kind of start us off here before we even get into the calculus, which we'll start talking a little bit about at the end of today's lesson, but we're going to focus on reviewing the properties of logarithms. So just a note about tonight's homework. So we're up to homework number 59. There is a PDF worksheet probably posted in your class notebook. You're going to go ahead and do the odd problems only on a separate sheet of paper. So make sure you go ahead and either print that out or locate that later today. Because we are focusing on reviewing the properties of logarithms, what we have given you in the first 2 pages of your notes is approximately 20 problems that are already done for you. Instead of having you, write them down, all of them as we go through them, we figured it would be helpful to kind of already have them done out, and then you could look at them and read through them at your own pace. We're going to go through a selection of them together just to kind of remind you of the 3 most important rules, and then you can go ahead and review the others on your own. And this is the majority of what tonight's homework is going to be about. You have to be able to do these properties of logarithms before you can then apply the exponential and log rules that you'll find on your formula sheet. So first, a reminder of some of the more basic properties. So if you were asked to find log base anything of 1, that would always be equal to 0. A reminder of why that's true. Really, when you're asked to evaluate a logarithm, you're being asked to find an exponent. So log base a of 1 equals 0. You could write that equivalently as a to the 0 is equal to 1. And that's why the property holds, because anything to the 0 power is, of course, always equal to 1. The second basic property you have to remember is that log base anything of itself is also equal to 1. Why is that? Well, if you go ahead and think about what it would look like exponentially, a to the first would, of course, be equal to a. You should also be able to evaluate simple logs that become integers. So, for example, log base 3 of 9. The reason why log base 3 of 9 is equal to 2 is because let's say you didn't know what it was equal to, log base 3 of 9 equals x. If you were to go ahead and write it as an exponential, and if you're wondering how I'm doing that, you may or may not have learned this using what's called the loop rule. There's lots of ways to know how to go from a log to an exponential, so however you were taught, feel free to go ahead and use that. But you would basically be asking yourself 3 to the what power equals 9, and of course that's why log base 3 of 9 is equal to 2. Notice that we would not ask you to do log base 3 of 10 or log base 3 of 11 because those are not integer answers that you should know. If I was to ask you for log of 1/10, hopefully you would remember that whenever you see an LOG with no base, that assumes that it's base 10. So this is log base 10 of 1/10 is equal to x. You would then essentially write that as 10 to the what is equal to 1/10. The only way that a 10 can become a 1/10 is if you move it to the bottom by making it a negative exponent, hence why it's equal to -1. And then again, hopefully you remember that when you see an ln with no base, you have to assume that that is base e. So ln base e of e to the third, let's say you're not sure what that's equal to. If you go ahead and write it exponentially, e to the x is equal to e to the third, and that's how you would conclude that x is equal to 3. So those are kind of the more simple, more basic things about logs and ln's that hopefully you should remember. Your calculator will also give you the same answers. And then most importantly, these are the big 3 that we're going to use the most. They are true not only for LOGs, but they're also true for ln's. Probably in the past, you did most of your problems with LOGs. Here in calculus, we are going to focus pretty strictly on the ln's, but please make sure that you know that the properties work for both. So property number 1, the idea that multiplication can be broken up into addition, that is of course called the product property. Property number 2, the idea that division can become subtraction, that is of course called the quotient property. And in number 3, the idea that you can take some exponent and move it down to the front, that is called the power property. So on the left side, you see it for the LOGs. On the right side, you see it for the LNs. Again, it works for logs of any base. And then there are two basic things you have to be able to do with these properties. You have to be able to expand expressions, and then you have to be able to condense expressions. So again, all the problems I'm about to go through with you are already in that PDF version of today's lesson, but we're going to go through all the evens just to make sure you understand what's going on. So because you're trying to expand these problems, that means that every single piece of the problem should be separated into its own log. Everything should be written as addition or subtraction. Simplify if possible, and all the exponents should move down to the front. So in this example here, log base b of t to the fifth, the only thing you're able to do is use the property, which says you're allowed to take the 5, move it to the front, to give you a final answer of 5 log base b of t. Obviously starting off very simply and then getting a little bit harder. In the next example, the ln of xy squared over z, the first thing you'll notice here is that the biggest operation that's going on is the fact that it's a quotient, which is a division. So the first thing we're going to do is use the quotient property, which says you're going to rewrite this as the ln of the numerator, turn the quotient into a subtraction of the ln of the denominator. Then xy squared, that is of course a multiplication. A multiplication can then be broken up into an addition using the product property. And last but not least, any exponent that's up front, you're going to move down to the front, which gives you a final expanded answer of the ln of x plus 2 ln y minus ln z. So again, when you're expanding, you want everything to be separated into additions and subtractions. Simplify if you can, bring all the exponents down to the front. A couple more examples. So please remember that the square root of something is, of course, equivalent to a 1/2 power. Because of the fact that both the x and the y are underneath the radical, if you're going to rewrite it as an exponent, you have to make sure that the x and y both get the 1/2 power. Because of the fact that the x and the y both get the 1/2 power, you're going to move the 1/2 out to the front of both of them. Then you're going to realize that this product xy can further be simplified into an addition using the product property. That would be a perfectly fine answer, or you could distribute to get 1/2 log base 3 of x plus 1/2 log base 3 of y. Those two answers are completely equivalent. And as we get deeper into chapter 5, you'll kind of know when is it better to leave it or when is it better to keep going. But for now, please make sure you know that those are equivalent. Ton of stuff going on in the next example, but the thing you'll notice most of all, yes, there are exponents, yes, there's multiplication, but at its heart, this is a division problem because the whole thing is being divided. So you're going to start by using the quotient property, which says you're going to do the log of the top minus the log of the bottom. Then you're going to take each of these products and break them up into additions. So here's the numerator being broken up into an addition. And then because you're breaking up the second fraction into an addition, but it's both after the subtraction, that's why we have to use that parentheses. In our final step, all of the exponents have to be moved down to the front. And I went ahead and distributed my minus to give me a final answer where everything is separated into additions and subtractions and all the exponents are down to the front. In the next example, and you can see they're kind of getting a little bit more complicated here, most of the examples we do in this chapter will probably be in the medium range, but I wanted to make sure that I showed you a mix. So starting off, log base 4 of 64, square root of x, square root of y, you'll notice that everything in this problem is being multiplied, which means the first step in terms of expanding is turning everything into an addition. Then, hopefully, you would realize that log base 4 of 64 can be written as 4 cubed. Each of these square roots can be written as a 1/2 exponent. Using the power property here, you would move the 3 down to the front. Using the power properties here, you would move the 1/2 down to the front. And this is one of our easier properties from a few slides ago. Log base something of itself is always equal to 1. 1 times 3 is, of course, 3, which is why your final answer would be a regular 3. The log is gone. 1/2 log base 4 of x and 1/2 log base 4 of y. Okay, so the opposite of being asked to expand logs is being asked to condense those logs or to express them as a single log. So it's basically the exact opposite of everything that we just did in the previous examples. So here you're starting off with a problem that is expanded using addition or subtraction, and you're going to try to turn it into a multiplication or a division. So because you have logs of the same base being added, you're going to go ahead and use the product property and turn it into a multiplication. In the next example, because you have a number out front, you're going to use the power rule, which says you can go ahead and move that up to be an exponent. In case you haven't caught on already, all of these problems only work if all the logs in the problem are of the same base. Please note that it's very unlikely that they will not be of the same base. We're not really trying to trick you, but we have to make sure you understand that they all have to be the same base in order for this to work. So here's our starting problem. We're going to go ahead and move all the numbers from the front up to the exponent. So this 2 moves up to an exponent. This 1/2 moves up to an exponent. And when we are condensing, we tend to write our 1/2 as square roots. Notice that the first 2 terms from left to right are being added, which means we're going to turn that into a product. And then finally, we're going to take this subtraction and turn it into a big old division. Again, your final answer should either be the log of one quantity, or it should simplify to be a single number. Here, we're going to go ahead and start by taking all the numbers from the front and moving them up to be exponents. Notice that the 4 belongs to the entire parenthesized quantity, x plus 3. Then note that I just did a little rearrangement here to put all my additions together and put all my subtractions in the back. Then notice that I took this addition and I turned it into a multiplication. And in my final answer, I want to have one single log base 2. And because this is a subtraction, I'm going to put my x cubed y in the numerator, and I'm going to put x plus 3 to the 4th in the denominator. So this would be my final answer. Okay, so now finally, we want to go ahead and talk about why we're going to need this information for chapter 5. So in chapter 5, we're going to be talking about the natural log function in particular to start, and we're going to start by taking derivatives. In this same chapter, we're also going to be doing integration, so you kind of have to make sure that you keep the 2 things separately so that you know what's what. So as you may or may not remember, throughout this entire process, never once have we asked you to find the integration of 1 over x. The reason why, if you're being asked to find the integration of 1 over x, you're essentially being asked to find the integration of x to the negative 1. If we were going to try to do that using the power rule, you would take the exponent, negative 1, raise it to the 1 higher power, and then divide it by that power. That would give you x to the 0, which actually would be fine because that's 1, but the fact that you're dividing by 0 is why that's not allowed. So it turns out that the power rule is no good anytime you try to integrate just simply 1 over x. There is a bit of a workaround for that. It's actually called the second fundamental theorem of calculus, and it allows you to make an approximation for the function 1 over x. We're going to be talking about something that we haven't yet talked about. It's not going to be algebraic. It's not going to be trigonometric, but in fact, it's going to be logarithmic. And more specifically, it's going to be the natural log. So from this point forward, if you are being asked to integrate 1 over a variable, 1 over x, 1 over t, 1 over u, whatever the case happens to be, that is going to be equal to the ln of x. Please remember that when it comes to natural logarithms, the domain has to be only positive real numbers. You're not allowed to take the log of a negative, nor are you allowed to take the log of 0. In terms of why you're able to use the natural log to estimate 1 over x is actually a little bit complicated. These next few slides are going to go through why it's allowed for us to do that. The truth is it's very nuanced. It's more of an AP topic. So if you don't completely understand why you're allowed to do it, that's okay, so long as in future lessons you can actually do it. So the reason why it's a good idea to use the natural log as a workaround here for 1 over x is because of the fact that you wind up getting all the positives and you wind up getting all the negatives. So in the left-hand side, it's telling you that if you consider any x that's greater than 1, you're going to get a natural log that is greater than 0, meaning you're going to get all the positive natural logs. If you have a value of x that's between 0 and 1, you're going to get a natural log that's less than 0, meaning you're going to get all the negatives. So because of the fact that you're going to get all the positives and all the negatives means you're basically going to get everything, which is why it's a good approximation for what we need here. Another reason why the ln of x is a good approximation has to do with something called a slope field. Again, you're never going to hear that word again in this class. You might hear it in a college class, but it's really more of an AP topic. This is the graph of the ln of x. Notice it kind of looks like a square root function, except for the fact that it travels all the way down the y-axis because, of course, there is an asymptote here. If you were to generate a slope field for the ln function, each of those little segments would actually have a slope of 1 over x, which is another reason why there is a connection between 1 over x and the ln of x. A couple other things to remember here. The natural log function itself, remember, has a domain of only the positives, but it has a range of everything. It's a continuous function, meaning there's no breaks. It's increasing the whole time, and it's 1-to-1, meaning it passes both the vertical and the horizontal line test. Please also note the graph is entirely concave down. Couple of other reminders about the ln, and remember when it comes to ln, it's base e. So the ln of 1 is always equal to 0, because if you had ln base e of what? Of 1, e to the what is 1, 0. Then, of course, you see our product property, our power property, and our quotient property. Couple more examples to show you why we're going to need to know these properties. If I'm going to eventually be asking you to take derivatives and find integrations, if I was to ask you to find the derivative of the ln of 10 over 9, that's actually a pretty difficult thing to do. But if you realize that you can break that up into the ln of 10 minus the ln of 9 using the quotient property, then it's a much easier problem. Similarly, in B, once you realize that a square root is equivalent to a 1/2, and once you move the 1/2 out front, makes that problem much, much, much easier to take the derivative of. In example C, first break it up into a quotient, then break the product up into an addition. Here, which is kind of as complicated as it gets, but again, at its heart, it is a division problem. So start by breaking it up into a subtraction. Take the exponent, move it down to the front. Take this product, turn it into an addition, but don't forget to use brackets because you have to distribute that minus. Go ahead and distribute that minus. And then in your final step, make sure that any floating exponents move down to the front. And again, for what we're going to ask you in chapter 5, which is to find derivatives and integrals, it is much, much, much easier to do from an answer like this as compared to a problem like this. So one last thing about the natural log function is that when you're using the properties to rewrite, you do have to double check the domain. So for example, if you were talking about the ln of x squared, because of what you could plug in and then square it, you could essentially plug in positives or negatives, which means the graph of the ln of x squared is actually twofold. Whereas if you use the power rule and bring the 2 down to the front, you're only going to get the positive version of the graph, which means that the domains are not equal. Again, that does matter in the future, not for right this second, but it's just kind of something important to keep in mind. A little last reminder here about the number e. So not only should you have studied logarithms before, but you should have studied base e. Again, the common log, if you see an log with no base, that is base 10. If you see an ln with no base, you of course have to remember that that is e. And again, some more about the natural log, that it's continuous 1-to-1 and has a range of all the real numbers.